So a lot of you maybe already know me. Some of you maybe don't know me. I have 2 minutes, too many slides, as usual, I would say, for people who know me. Ang mentioned that she come from composite this morning. I also come from composite at the origin, so working on ceramic fiber reinforcing ceramics, so I say composite. And I work a couple of years after on that composite. But at a given point 30 years ago, for some reason, I was hesitant to move in refractory area. And to make the link with composite, you will see during my presentation that I try to make the link with composite from my background. And I will try to produce you a teasing, I would say, because 45 minutes is not so strong to go in details. Nevertheless, I would like to show you a couple of things in order to try to interpret in a better way the results that we can obtain from Young's modulus measurement versus temperature, because this equipment has been spread a lot in a lot of companies now, and you can see curve which is rising, decreasing, and so on. So you have a lot of evolution with this curve. And of course, you can describe this rising evolution or decrease, but it is much better if you are able to go inside the microstructure and to be able to try to interpret this kind of thing. But of course, refractory is a very complex world, I would say, and this is very often extremely difficult to make this link with the description of the microstructure, because many things occur inside initial component of refractory, and after that there is a lot of interaction with surrounding slag and so on, gaseous species, which change completely the things, and then it's come a nightmare to understand what happens there with thermomechanics. Nevertheless, I will try you in this 45 minutes to draw some key line. And after that, you should see that as a teaser. There is my email after that. And then you can contact, of course, all the teacher for this session. I see some guy taking some picture. You have also the USB in your bag with all the presentations. So you can take picture, of course. I have no problem with that. But you will have better presentation with the USB key in which there is all the presentation of that you will follow during this session. Okay, so a lot of slides, 33. But I will try to give you very raw idea coming from my composite previous experience. So introduction. So effective property of elasticity, strength, thermal expansion. So as Dietmar, I am very concerned with thermomechanics. So I try to understand how we can do better with the microstructure and optimizing the microstructure of the material at its initial state. After that, we have to take into account the interaction of the atmosphere, which becomes much more complex. But nevertheless, we have to try to do that to understand. And starting from the intrinsic property of the component, so as a composite, seeing the refractory as a composite. So you have seen already this key formulation. If you already go in thermomechanics, you have seen the key paper of Kingery, Hasselmann. They have produced a lot of things in the 60s, and many people refer to that work after that. So that's good paper for sure, but there is many things that has been done later. But it is good basis. And I have more concern by all the parameters which are inside this formulation, especially Young's modulus, but also all the other strengths, strain, thermal expansion, and so on. So I will more focus about the primary property which is included in this formulation. So property at very local scale. So I will not bother you with probably lectures that you have already followed in your previous curricula with mechanics, so tensor and so on, but nevertheless, this is the basis. And of course, I will not go in detail, but this is just to remind you that if we think in terms of crystal, the crystals are not isotropic, and then you have to consider the anisotropic behavior of those single crystals inside the microstructure. I'm not here to bother you with tensor, but nevertheless, this is there. So I will not go into details about the reduction of indices and so on, but it should remind you a couple of things from your previous background, and these aspects are still there. And if, again, this is linked to the potential, atomic potential, and of course there is strong link between the atomic potential and especially the Young's modulus, because the Young's modulus is directly linked to the second derivative of the interatomic potential. So if you want to have high value of Young's modulus, you need to take care about the atoms you put in your system in order to increase the Young's modulus. Maybe high value of Young's modulus is not a good target, but nevertheless you have to play the game with the different species in the Mendeleev table, and to play your game in the right area. Of course, if you play with silica, this is not the same story if you play with silicon and carbon, because of course the interatomic potential are absolutely not the same. Of course, after that, there is the theoretical strength, which is still there. Of course, there is a lot of modification induced by defect due to Griffiths. You have learned that in your background. Of course, but you have nevertheless to remind that the basis is theoretical strength, and after that, this is modified by the defect. So, elastic property of crystal is described by tensor. You have to live with that. So, of course, elasticity of alumina is not a simple value. You have a lot of value which describe the elasticity of alumina due to the trigonal structure of this crystal. I just take the occasion to draw all the things that you can find from literature for the crystal value of alumina, taking into account the trigonality. So the elastic property of alumina, elastic property of silica, you can see this is much lower. If you look at mullite, this is in between. If you look at magnesia, this is also in between. Spinel, this is also rather similar to magnesia. But in both cases, this is cubic, so we are quite lucky. Then this is much more simple with only 3 elastic constants. If you look at about andesite, which is a mineral I like a lot due to many things, which is orthorhombic, you have to play the game with different elastic properties. Okay, so from single crystal to polycrystal, you have to combine all those things, and you can find also in literature the work of Voigt, Royce, and Hill, and all the formulation which allow you to calculate an average value of a randomly oriented crystal, which in that case, if you look at the grain of aluminum which become isotropic due to the random orientation of each crystallite, then you can consider that this is an isotropic material, even if the crystal, at the crystal scale, this is a non-isotropic material. So it could help you to move to the intrinsic property of each crystal you consider, each polycrystal that you consider as a pure system without any porosity. And this, maybe it could be interesting to keep that value in mind, because these values are absolutely the value that you should obtain if your material doesn't contain any defect, any crack, any porosity, any other things. If you have a pure material, fully dense, you should be at this value. If you are not at this value, it means that you are far away from that due to many different things. Of course, in refractory, you are never at this level. But you have to interpret why you are not at so high level, depending of the process, depending of the history of the material. And this is here that starts the interpretation of the result. But this table is a good reference to keep in mind where you should be if you would have done a great job having a fully dense material, pure, without any other things, any microcrack and so on. After that, of course, you usually, due to the compromise that you have to do, you have already seen by the presentation of my colleagues, that refractory world is always a compromise. You need to play something with alumina, you need to introduce some spinel, some many other things, and then it becomes a mixture of something, which becomes very complex. The first mixture role, and this is also very popular, this Voigt and Royce formulation, which is quite simple. So I will not refresh your mind about that, but this is typically mixture law, what we call mixture law, and which is very often used in paper. Because this is very easy to apply, I would say. But in fact, this is not because this is very easy to apply that this is true. Because in many cases, this is not exactly true. But nevertheless, in many papers, we want to interpret the result. Most of the people use this formulation, mixture law, which doesn't work, in fact. So take care about that. I would prefer much more complex formulation, you can find also in literature from Ashin and Strickman in the 70s. And in fact, this formulation works well. Of course, this is much more complex to introduce that in Excel, but nevertheless, this is a formulation which works well. Because when I went in refractory area 30 years ago, I come from composite, so I was very familiar to do these kind of things, and I tried to understand why we are not at the right level with this very complex composite of refractory, and I tried to understand why this is very difficult to understand, and we start finally with very simple system. We build our own system in order to check where we should be if we can do a good job of producing composite. And if we do that, this is what we have done typically 30 years ago, working with composite and bending bed of alumina inside the glassy phase. Of course, it is very far away from refractory area, but nevertheless, to fix the area in which we should be. And in that case, if you elaborate a material which you can see as the composite, a fully dense composite glass in-bending bed, then in that case, the formulation which works well is Ashin and Strickman minus. Why this is that? Because typically in most of the refractory materials, the bonding phase is typically less stiffer than the aggregate. And then in most of the refractory system, your bonding phase is less rigid than the aggregate, and then you can consider that the Ashin and Strickman minus is applying very well to describe your system. And then you are far away from rose, you are far away from void, in fact, and the good prediction is typically this formulation, so typically this one, which is a little bit complex, but this is manageable. So from that, we can also consider, of course, more recently, a lot of numerical calculation using finite element modeling. More recently, we have done a lot of things using discrete element modeling. I will not present anything about discrete element modeling, but if you participate to ECerS Congress, you can see a paper from Harry about that. But typically, the key point here, if you do numerical modeling to describe microstructures, the important point is to consider the right boundary condition. So typically using periodic boundary condition in order to mimic the large structure of the material in good conditions. So the periodic boundary condition is a key point in order to describe the property, because in that case, if you use really the periodic boundary condition in modeling, you are able to describe a quite large system, even with very small amount of inclusion, because it works with only one single bed. It can describe perfectly your system in that case. And this is very simple, quite simple, I would say, in modeling. We can do that also in DRM, but this is well known in FEM modeling. I will skip that about anisotropy. I will skip that. And then, of course, in that case, you can see here, so typically homogenization technique using different capacity system and using periodic condition. And this is typically in comparison with real experimental data, which is very close to Ashin Strickman minus, which confirms the fact that Ashin Strickman minus is a good model, analytical model to describe a perfect composite system. So again, this is the same thing in today. I will not go in detail. Effect of porosity. Of course, most of the refractory materials are not fully dense. Then you have to account for porosity, and then you have to place your theoretical value, taking into account the porosity that you have evaluated by different mean. And of course, the effect of porosity, a lot of work has been done by a colleague, Willy Paps. So he's well known in that area. He has produced a lot of paper even recently. And I encourage you to follow the work of this colleague in Prague. And this is typically so model. So you can use different models. So of course, the void bond is this one, which is typically this one. No, this one. You can see that the void bond is absolutely out of the scope, so you should forget that. There is many other expressions. So this one, and this one. Well, this is not so far from each other, but typically, Ashin Strickman is also not so bad, but not so good, no, also. So typically, this exponential work quite well. And In fact, after that, there is other author who has taken into account, it depends of, in fact, for the porosity, the key point is depend of the shape. If the porosity is round, you can apply different specific model. So typically the one that I presented in the previous slide. But if your porosity is not round, which is the case in most of the case of in refractory area, you are not there. And then the classical model is not exactly applicable. I will skip this slide, I think. About pressure ratio, I will just move to those ones. So if you, about the geometry, there is some author, yeah, so this is a paper from 2000. There is more recent paper from Willy Paps about that. And you can see if you have overlapping spherical pores, so typically distribution of porosity like that, you are there. If you have more tortuous porosity, you are far away, and you have a decrease in elastic property, which goes much faster. And of course, in case of refractory, if you look at the shape of the microstructure, you are far from sphere, and then that means that the porosity will decrease a lot your elastic property. And Willy Paps has made very interesting paper in recent year. So typically playing with quite round porosity, and then in that case, with quite round porosity, the model is not so far from the picture I presented you just before. But if you put porosity in completely other shape, and then the story becomes very different. And then you can see here, in that case, the porosity is very elongated due to the construction of the model. And if you look at where you are here, which is far away. And this is then the evolution of the incidence of the porosity is extremely dependent to the shape. So if you want to predict where you should be in terms of elastic property, you have to take into account the amount of porosity, but also the shape of the porosity, considering this kind of model. Effect of microcrack. So if for the people who know me very well, you know that this is my motto for research since typically 20 years. So we work a lot on material containing microcrack, because honestly, today I consider microcrack is part of the design of the material. So typically when we discuss about thermomechanics, typically microcrack should be there to tailor the property for thermomechanics. And this is an important part of the material. It weighs nothing in the component, but it plays a key role in the end in the thermomechanics and in many areas of the thermomechanics. So this is absolutely crucial in many cases for thermomechanics, for Ledelswood, for many applications in which refractory are confronted to huge thermal shock. You need to put in a very tailored way microcrack in your design, and this is a key point to obtain the pertinent thermomechanical property you would like to obtain to sustain the condition of application. And of course, people who start to work on that topic is quite, so a lot of work has been already done far away, so typically 30, 60, 50 years ago. And you can see here interesting formulation coming from Hasselmann again. So Hasselmann was very productive during the 50s and 60s. And so typically he describes the macrocrack with typically a penny-shaped geometry with the size A, and he introduced the size in the parameter and the density of those cracks, and the definition of the density is typically the count, but the count taking into account also the size. So this is the density considered in the formulation. The formula are quite complex. But in fact, of course, you have seen by Dietmar the R quadré parameter coming from the thermal shock parameter from Hasselmann. But behind this R quadré, there is this formulation of evolution of Young's modulus. If you look at the original paper in the 60s, you have exactly this formulation, which is taken into account in an energetic balance of Hasselmann. So this is quite formulation are not so simple, but not so complex. There is a pressure ratio, there is a density here, and you can see that if you consider the property of if you have cracks, which is not randomly distributed. So typically, if you have crack in that direction with a plane in that direction, if you measure the property in the same direction to the crack, normally, theoretically, there is no change in elastic properties. You have crack, but there is no modification of the elastic property. Of course, if you consider the elastic property in the perpendicular direction to the plane, this is completely another story. And then this is exactly what is considered here. So if you have a K0 value, K0 means that you consider that you are measuring the elastic property in the parallel direction to the plane. There is no incidence in the elastic property. But if you consider the elastic property perpendicular to the plane, this is completely another story. And you have a huge decrease in elastic property depending on the density. After that, an interesting thing is also the pressure ratio, and we have still discussion about that with the measurement of pressure ratio in microcrack material. This is not extremely well documented in literature, but nevertheless, of course, usually in refractory, pressure ratio is about 0.2, between 0.25, 0.15, and you are playing in this game. But in some case, you make measurement and you find 0, and you will find in some case minus 0.1. Oh, what is this surprising measurement? And it happens quite often. I'm looking for that now. It happens quite often to have a very strange value of pressure ratio. And there is still open question here about the measurement of this crazy value, but nevertheless, if you consider the value, the model, they also already describes a decrease in pressure ratio versus the number of cracks. So this is already documented in literature from this analytical formulation. After that, of course, if you look at about macrocrack, you have to consider the damage. So with the Kachanov parameter, I'm sure that if you have done micromechanics, you have considered this Kachanov parameter in your background. So there is definition about that. I will not go too much deeper in that, but of course, you have to consider that Kachanov parameter, so the decrease in elastic property due to the presence of macrocrack. And of course, if you load the material and if you don't have any cracks, then the damage parameter is starting at 0. And as soon as you increase the number of cracks inside your system, you increase the damage parameter, and the maximum value will be 1 when you will fully break your system. So damage parameter is typically a parameter between 0 and 1, and which typically is completely related to the introduction of cracks due to many things. It could be thermal shock, it could be mechanical loading. And if you look at, if you implement that in mechanics, you can implement an isotropic damage parameter, but if you consider that the crack could be oriented, you have to take care about the orientation of those cracks depending of the loading. And then, instead of having an isotropic parameter, you need to introduce, again, a tensorial parameter to take into account the orientation of the crack depending of the load that you have applied in a given direction. So you can see here that, of course, if you play the game here, there is no evolution of damage. If you go to this point, you have an improvement, an increase in the damage. And interestingly, I just picked up some results from Renault. So you have seen a presentation about wedge splitting this morning, and you can implement that in the wedge splitting test. And you can see if you implement the damage evolution in the wedge splitting test, you can see the evolution of the different damage parameter considering a tensorial damage parameter. So depending of the stress direction which takes place inside the wedge splitting sample, you are able to monitor the area in which you have a huge increase in the damage parameter, and you can see that in some directions there is no damage because of the configuration of the wedge splitting test. So this is also interesting to see how the material behave under mechanical or thermomechanical loading. Maybe I will skip this slide. Effect of temperature. Of course, the key point of all the point I mentioned today is coming from, because I come from composite, I mentioned before, and when we start to do measurement of Young's modulus on refractory material 30 years ago, and it was on Vesuvius material, alumina carbon for Ledelsrud. The curve was rising, decreasing. There was a lot of things, and it was a nightmare to understand what happened on this curve. We were here, okay, so it was rising, decreasing. We were able to compare one material to the other, but completely impossible to interpret the result because it was so complex. And then we decided to put a more scientific framework behind, working on model system, and then come back a couple of years later in order to interpret the result. So typically, if you look at conventional crystal, so all the components that you put in your material, typically should see an evolution which is typically linear decrease versus temperature in the classical temperature range between room temperature even to 2000 degrees C. So normally you should have a straight line. If you mix alumina with magnesia, with spinel, normally you should have a straight line. If you mix, you have a composite with a decrease versus temperature, which is linear, and you should have more or less a straight line. So typically measurement on dense alumina, you have typically, well, this is not exactly a straight line, but not so far. But if you look at material, refractory material, this is far from that in many cases. And this is at this point that the interpretations start to be more complex. So if you pass a castable, the evolution of the curve becomes very much more complicated. And just to facilitate your interpretation, if you have a RFDR system, I will speak about measurement after. Looking for the time, 10 minutes. Oh, maybe I will be good. This is not usual for me. Okay. Dense alumina again. So typically you have a evolution of atomic potentials. You have a decrease in the bonding of the atom. Then you have a decrease in elastic property, and you have typically a reversible decrease. But usually you have this kind of thing, which is also of importance. You mentioned glassy phase. In fact, I believe, I have no proof, but I believe that in most of the cases when we are observing that, this is something that happening at the grain boundary, which is due to the very small amount of magnesia which is there, and which should probably decrease in a reversible way. And this is typically the signature of, I believe that this is the signature of the small amount of components which are at the grain boundary. Because if you do that in a pure polycrystal without any additive, I have never been able to do that. Normally, you should not observe that. So it could be also an interesting point to, as a kind of signature of some small element which are being introduced in the raw material by Alteo or so on. If you look at glassy phase, this is a special case of glassy phase. In glassy phase, usually you have a glass transition, so you probably were very familiar about that. So glass transition, you have a huge transition in thermal expansion, and you have also a huge transition in elastic property evolution. So this is typically the signature of a glass transition. And in that case, this is a glass which is subjected to recrystallization because this is an hydrogen glass, which is designed to put that in the boundary phase in silicon nitride. And then you can recrystallize. And then if you come back with a material which has been fully recrystallized, you have no more glassy phase. And you can have the proof of that because there is no more glass transition as a signature of the curve. So this is also a good indicator to see if you have still a small amount of glassy phase or not. In that case, there is probably not so much glassy phase. Same thing, glassy phase in the silico-alumina glass. Yeah, so same thing. You have also the attenuation, the Q-1. If some of you is measuring thermomechanical property with the RFDR system, you have a Q-1, which is also an interesting factor, which is linked to the absorption of energy by the component which is becoming more viscous. And materials that I like very much, aluminum titanate. I play with this material a lot due to the thermal expansion mismatch between the different crystallographic axes. And in that case, this is very curious material because you start at typically in that case 40, which is the low value, but it moved to high value of Young's modulus, which reach more than 140 at high temperature. And this is just because of the crack which is inside the microstructure of the material as a starting point due to the CTM mismatch. And this is a material which is well known for thermoshock because of the quantity of macro crack which is introduced in the material due to the CTM mismatch between the different crystallographic axes of this orthorhombic architecture. And this is a very pedagogical curve to demonstrate how a material behaves when you have a material which is not subject to any evolution in chemistry, not subject to any evolution in density, in porosity, just cracks evolution. Just crack evolution, you have a perfect signature of an hysteresis curve, which is a typical signature of the material containing cracks, which is, of course, for conventional guide in mechanics, usually cracks is bad and decrease the property, but for refractory guide in thermomechanics, crack is a good point, and you should have crack, and you should play with crack. So indirect effects. So typically we have played with that due to that aspect. So we start typically with alumina carbon material from Vesuvius, so typically 30 years ago. And in order to understand better the things that are running on those material, we play with those systems. So it was a motivation starting from alumina carbon material to go in that direction of model system in order to understand better the role of macrocrack. And then in that case, we have elaborated different composite material, modifying the chemistry to tune the value of thermal expansion of the glass to generate different kind of system. In that system, we generate a material which lead to debonding, not cracks, debonding. That means that the glassy phase, which is used as a matrix, as a thermal expansion, which is significantly lower than the alumina bed. And then when you, after sintering, when you cool down the material, you generate debonding. And in that case, due to the debonding, the Young's modulus is not at the level it should be with the Ashton-Strickman model. So you start with debonding, so the material exhibits a significantly lower value of Young's modulus. But when you reach the temperature of sintering, you close the debonding, and you come back to the Ashton-Strickman value. And then when you are close to the Ashton-Strickman value, it means that there is no more debonding between the alumina bed and the glass matrix. If you play the opposite, if you change completely the chemistry of the system to have a thermal expansion much larger than the alumina bed, this is completely another story, because in that case, you generate a lot of cracks. And then the Young's modulus is much lower. And then, but you have, again, the signature of a closure mechanism and a reopening mechanism. Of course, you can see also that the closure mechanism is a little bit more difficult in comparison. If you compare a crack material and a debond material, you can see that the way the material close the crack is more difficult in case of macrocrack in comparison to debonding. And it can be easily interpreted because the shape between the different parts of the bond is much more easy to interconnect in the case of debonding in comparison to macrocrack system. A classical observation in completely other area of application of refractory, so this is typically cordialite mullite. So in order to reinforce creep, usually refractory producer of those products introduce mullite in order to reinforce creep. But in that case, you have after that a composite which contains a cordialite matrix in bending mullite aggregate, and again you can say a perfect signature of an hysteresis corresponding to debonding between the cordialite matrix and the alumina inclusion, which is here for creep. And interestingly, there is also an interesting point with the curve of thermal expansion. Because as soon as your mullite is completely isolated from the matrix, then at the beginning of the curve, you have a fully cordialite system with no mullite there, because the mullite is completely disconnected to the rest of the system. And then you have a very low value of thermal expansion, despite the fact that you have mullite. And of course, as soon as you eat, you reconnect the mullite to the system, to the matrix, and then you increase the thermal expansion. And then the mullite could play the key role for the creep. But it deteriorates not so much the thermal shock behavior of the material, despite the fact that the thermal expansion of mullite is much higher than cordialite. Same thing for magnesia spinel material. Of course, Dietmar, you mentioned also this material, so we play together the game 15 years ago. So typically, the interesting point of what I mentioned just before, if you are very clear about the components which are in the system, you can see here you have a full system constituted of magnesia. Okay, you introduce aggregate, and we have measured a full magnesia brick, which is there, a spinel aggregate. We have done the measurement on the spinel aggregate. If you introduce spinel aggregate inside the magnesia matrix, using Ashton-Strickman model, you should be on those lines. But in fact, you are not on those lines in design, because the target, of course, is to have spinel, but behind the spinel, the target is to introduce microcracks. And then with the distinction, if you quantify the gap between the dot line and the real measurement, this is typically the measurement of the macrocrack inside the system that you have introduced thanks to the presence of spinel. And this is voluntarily introduced because we want to increase the fracture energy. So in that way, you can have a quantification of the damage if you know exactly where you should be without any crack. And if you do the measurement with crack, then you are able to make some quantification in a precise way. Of course, if you hit the system, you have, again, an hysteresis curve. Of course, this is not so beautiful because you don't close the crack in a perfect way in that system in comparison to the previous one. Nevertheless, you have still, an hysteresis curve which demonstrates that you have a closing mechanism. But nevertheless, you can, with the mathematics of the model, you can clearly demonstrate that the cracks are not fully closed at high temperature and far away. So because you are far away from the theoretical value predicted by Yashin-Strickman using the component of the system. And then you can justify the fact that, yeah, you are not able to close the crack even at high temperature. Of course, playing with those kind of systems, this is very interesting to check all the different value of thermal expansion. I also incite you to check more carefully thermal expansion value because usually people consider, okay, thermal expansion value of alumina should be about 8 or 9. But in fact, if you look at carefully the documentation, this is absolutely not like that because the thermal expansion is not constant and depends on the temperature range. And if you look at the thermal expansion of alumina, in fact, it starts at 8, yes. But in fact, if you look at the value at high temperatures, this is much larger than 10 because this is not constant. The thermal expansion is not constant. And of course, after that, depending on the crystallinity of the material, if you look at material which is probably, for example, orthorhombic, which is the case of all these constituents, you have some chance to have a big gap between the thermal expansion in the different directions of the crystal. And it could be of interest to design material, especially in the case of aluminum titanate. I show you some aspect about that, but it's also interesting in the case of andesite system. Okay, so the same thing with alumina. Alumina is very famous, okay, but alumina exhibit also thermal expansion mismatch. Not so huge. If you look at the previous value, alumina, yeah, alumina is in French, sorry, but you can see, okay, or you can consider, okay, this is almost the same thing. Okay, these two red curves is very close to each other. There should be no problem. But in fact, no. No. Because of this very small difference, if you play with large grain, you are confronted to thermal expansion mismatch in alumina. And this is a famous paper which has been published a long time ago, and in which, if you play with large grain, you can see this curve which has been published 45 years ago, and which demonstrates that if you have large grain in alumina, you can have crack. Okay, so of course you have no crack in alumina if you are sure that the grain remains small. But if the grain becomes quite large, around 50 micron, you can have some chance to have crack. And this is completely demonstrated in literature. Aluminum titanate, I already show you this curve. I'm looking for the time. Okay. Interestingly, the thermal expansion curve. The thermal expansion curve of the crystal is fully linear, fully constant. The thermal expansion is fully constant versus temperature if you look at the thermal expansion by X-ray measurement at high temperature. So normally, if you consider polycrystal, you should have a straight line. But in fact, you can see the strange curve, yeah, which is coming from microcracks. This is typically a caricature of curve of material exhibiting macrocrack. I have shown you before a slight change in slope in cordierite mullite because the change in thermal expansion is not so huge. But in case of aluminum titanate, this is the signature of the thermal expansion. When you look at the thermal expansion curve the first time, it becomes crazy to understand this curve. And the important point, which is connected with work of fracture, due to the crack, you are able to enlarge the fracture energy. Of course, this is in this case, this is in tension, measurement in tension. We have done some measurement, quite recently, measurement in mini wedge fitting in Leoben. We have demonstrated that we have an increase in fracture energy. And so there is different parameter which makes this material a very good candidate for thermoshock. If you look at the intrinsic property as the crystal, okay, with an average thermal expansion of 10, you should forget thermal expansion application with thermal shock. But in fact, no. the thermal expansion in average is quite huge, but due to the micro crack that you can play with in this system, it becomes a very famous material for thermal shock because of the cracks that you can introduce due to that. Andesite, this is again andesite with single crystal. Thermal expansion mismatch between the different crystallographic axes. You can see the hysteresis corresponding to micro crack closure opening, and you can see the consequence of the introduction of cracks. You have a decrease in strength. So as mentioned by Dietmar, strength is not the target when you play with thermal shock. You should not forget that. The strength is not your target. Your target is fracture energy, reduction of thermal expansion, and also enlargement of strain to rupture. And in that case, you have all those points, which is in a good shape. Very quickly to finish with 2-3 minutes. Just to highlight, okay, so in literature, you find dynamic measurement, static measurement of elastic property. I should admit, I'm not a fan of that. This is very present in literature, especially in refractory. But usually, when people mention, in my opinion, when people mention dynamic measurement and static measurement, this is because they don't understand what they measure. And if you look at what you measure and if you take care about your measurement, normally you should obtain the right value of elastic property, and the same for the different experimental devices. What I explained, if you do measurement with ultrasound, typically the strain that will be engaged in the measurement will be very low. And then you will not damage your material if you propagate ultrasound inside your system. And then you have a lot of chance to obtain a higher value of Young's modulus with ultrasound. If you play with, well, I will not go in detail about the formula. You can check that later. Maybe you have RFDA system. In RFDA system, you make an impulse and you make the resonance measurement. It has some similarity with ultrasound, but in fact, when you hit with the hammer here, the amplitude of strain that you engage in your measurement is not exactly at the same level that you engage with ultrasound. And then you have to take great care about the energy which is applied with your hammer, especially when you are in front of macro crack material, because if you hit the system, you can generate additional crack inside, and then you measure things which are different to ultrasound, because you engage damage in your measurement. Then you have to take, even if the hammer is not so heavy, it can modify the structure of the material if you hit too much your sample. And then we are focusing now very deep inside measurement at very low energy with okay. In order to take care about that, reducing the energy engaged in the measurement. If you do measurement with mechanical test, you have no choice because of the sensitivity of the equipment. You require high level of strain, because if you would like to measure something, you need to go above your resolution of your system. And then in that case, you have a lot of chance to engage defect inside your system, and then you measure things which are different in comparison to the other technique. So my belief is that normally there is one Young's modulus. If you take care about the measurement you are managed, you should obtain the same one with a different equipment. Of course, this is not an easy task. This is not an easy task, but of course, if you compare mechanical test with what we call dynamic, I don't like this term. This is because you engage different strain level, and then the result in the material is not the same. And I will stop here, because you can see comparison here between ultrasonic and ultrasound, and I will finish with this one. Comparison with mechanical tests, between mechanical tests and echography. If you do a very good job, normally you have the same value. But as soon as you move at high temperature, you will have creep. And then, even if you do your best job, you are killed. You will never measure the same thing, because why? Because in that case, you have already creep, you have already viscoplasticity, and you are not measuring Young's modulus anymore, because you are at high temperature with some silica, and then you measure other things. So if you compare, take care about the experimental condition. That's it for me. Okay. Thank you.